the previous talk by Daisuke Sagaki. And this is a joint work with Shukato at RIMS and Daisuke Sagaki at Tsukuba University. So, yeah. So you already know the basic definitions about MV polytopes or Demazure crystals. We omit its explanation. So, let's give the estimate of tensor products of MV polytopes. Now let lambda 1, lambda 2 be dominant co-weights and P1 and P2 be MV polytopes. Suppose now that under decomposition of this tensor product, MV lambda 1 times MV lambda 2 into connected components MV lambda with multiplicity M lambda, lambda 1, lambda 2. Then now we suppose that we have P1 times P2 is in MV lambda for a unique reducible component MV lambda with a dominant co-weight lambda such that M lambda, lambda 1, lambda 2 is greater than or equal to 1. Now our first main theorem is this. Assume that the MV polytope P2, the second factor, is an extremal MV polytope. Then we have in HR P1 times P2 is contained in P1 plus P2, where P1 plus P2 is a Minkowski sum defined in this way. And here P1 times P2 is considered as an element of MV lambda for some lambda above this. Yeah. We will explain about this, the proof of this theorem later, but the approach is geometric. We postpone it, and we first give one combinatorial approach using this result. Now, so let lambda 1, lambda 2 be dominant co-weights. Then we have an embedding iota lambda 1, lambda 2 from MV lambda 1 plus lambda 2 into MV lambda 1 times MV lambda 2 of crystals, such that iota lambda 1, lambda 2, P lambda 1, iota lambda 1, lambda 2 sends P lambda 1 plus lambda 2 to P lambda 1 times P lambda 2. And let P1 be an element of MV lambda 1, P2 be an element of MV lambda 2. These are MV polytopes. Be such that P1 times P2 is an element of this connected component, top connected component. That is, there exists some P which is an element of MV lambda 1 plus lambda 2 such that iota lambda 1, lambda 2 P is equal to P1 times P2. Then we have a corollary of this theorem. We of course obtain the following. Assume that the MV polytope P2 is an extremal MV polytope. Then we have in HR P is contained in P1 plus P2, where P1 plus P2 is a Minkowski sum defined by this. And P is such that iota lambda 1, lambda 2 P is equal to P1 times P2. And we use this corollary later. Second, we introduced the notion of n multiple maps for MV polytopes. Let lambda 1 be dominant co-weight, and for positive integer n and an MV polytope P, we set n dot P, which is defined by this. And then this set is equal to the Minkowski sum P plus P plus dot 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 plus P. These two sets are equal. This is not at all obvious, but we can prove this equality. And we have the following proposition. Let lambda be a dominant co-weight and if p be an element of mv lambda and n a positive integer, then we have n dot p is an element of mv n lambda. From this, this proposition can be shown directly by the definition of this map and some properties of IMV polytopes. And from this proposition, we obtain an injective map called an N-multiple map, denoted by Sn from mv lambda to mvn lambda by this Snp. P is defined to be n dot p. Moreover, we obtain the following proposition. Let lambda be a dominant co-weight, and for p be an element of mv lambda and n a positive integer, we have the following. The first is weight of Snp is equal to n times weight of p, and for each index j in I, Sn ejp is equal to ejn Snp, and similarly Sn fjp is equal to fjn Snp, and for each index j, epsilon j Snp is n times ejp, and phi j Snp is equal to n times phi jp. But unfortunately, Satoshi doesn't explain this notation, epsilon j and phi j. So epsilon j is defined to be the maximal integer n. Ej of k, ej of p is defined to be the maximal integer such that ej kp is defined. And phi jp is defined similarly. Now let us introduce the following notation. Let lambda be a dominant co-weight, and for a positive integer n, we denote by kn, which is a map from mv lambda into mv lambda times n, which is a tensor product, mv lambda times mv lambda, n times tensor product, which is defined to be the composite map of the n multiple map defined above with the canonical embedding of mv n lambda into mv lambda times n. First, we map Sn mv lambda into mv n lambda, and then mv n lambda into mv lambda times n. And composing these two maps, we obtain a map from mv lambda into mv lambda times n. Note that this is not crystal embedding, of course, because we have this. Now, for this map, we have the following trivial remark. Kn p lambda is equal to p lambda times times p lambda, n times tensor product. And now we recall the following notation for lambda, a dominant co-weight. We denote by w lambda min, the set of minimal length set representatives for w over w lambda, where w lambda is the stabilizer of lambda in w. Namely, we have this bijection as a set. So now the following proposition. We have the following important proposition. Let lambda be a dominant co-weight, and let x be element of this w lambda min, a minimal length coset representative. And let us denote, we call mvx lambda, mv sub x lambda, the Demazure crystal, associated to x introduced in Sadaki's talk. And if P is an element of this MVX lambda, then there exists some positive integer n containing sufficiently many in the sense of Professor Kashiwara. And such that KNP is of this form, which is a tensor product of py1 lambda times py2 lambda times dot 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 times pyn lambda, where y1, y2, dot 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 yn are minimal coset representatives W lambda mean. And we have this property in the Boolean ordering on W. X is x, y1, y2, and yn. And these elements are all less than or equal to x. Yeah.
The condition you serve always you have this phenomena over this.
Yeah.
When you take sufficiently.
Yes. Sufficiently, but so if we find one sufficiently, if we want n, then all multiple of n is okay. But only the inequality is not sufficient. And so the important point is containing many divisors. Yeah. So now we remark relation with LS path. If we denote by pi the Lakshmi-Sheshaduri path, LS path of shape lambda corresponding to the MV polytope P under the explicit, this is the 1 point isomorphism crystals, which is obtained via the crystal base B lambda. Then the vectors above y1 dot lambda, y2 dot lambda, yn dot lambda give the direction of the LS path, where the LS path is considered to be a piecewise linear continuous map from this interval to the real form of the Cartan-Sava algebra of G. So here, so LS path is like, and final point is weight of pi. And these vectors are w1 dot lambda, w2 dot lambda, w3 dot lambda, and so on. These are the direction vectors of this piecewise linear continuous map, which is drawn in HR. Then, then.
You mean that you can only determine the direction, not the rational numbers AIs?
Oh, well, they are rational numbers, of course, or divided by.
Lakshmi-Sheshaduri path is defined by the piecewise the elements of while groups and some rational numbers.
Yeah. And they are obtained by k over a large n, where k runs from 0 to n.
So you actually determine the Lakshmi-Sheshaduri.
Yeah. So, in fact, also, if we write the path pi of shape lambda in this way, where nu1, nu2, nu_s are elements of the while group of W lambda, and A0, A1, AS are rational numbers, then any integer n such that this condition holds suffices for the proposition above, the proposition of this proposition for n. This condition is enough. Yeah. Now, oh. So now give a polytopal estimate of every polytopes lying in a Demazure crystal. Let lambda be a dominant co-weight and W lambda the stabilizer of lambda in W, and let X be a minimal coset representative modulo W lambda. And we denote by MVX lambda the Demazure crystal associated to X. And let P be an element of this Demazure crystal, then by proposition above, proposition, this proposition, we have a positive integer n such that KNPs of this form, py1 lambda times py2 lambda times pyn lambda, which is an element of mv lambda times n. For some y1, y2, yn satisfying this condition in the Breuer ordering on W. Now we use the polytopal estimate of tensor products of MV polytopes. We call it this theorem, or its corollary. This corollary. N times, or n minus 1 times. Then we obtain this inclusion relation. So by dividing by n both sides, we obtain this, and in particular, if we recall that, and so we obtain this polytopal estimate of MV polytopes by, we recall that the vectors y1 dot lambda, y2 dot lambda, yn dot lambda gives the direction vectors of the LS path pi of shape lambda, corresponding to the MV polytope P under the an explicit isomorphism. So, this is only an inclusion relation, not the equality, but at this moment we have only this, but we want to refine this result in the future problem. But anyhow, this is enough for our present purpose. So now we recall from Sawaki's talk the following polytopal description of extremal MV polytopes. Let lambda be a dominant co-weight and y be a minimal coset representative. Then the extremal MV polytope py dot lambda of weight y dot lambda is identical to the convex hull of the subset, this subset, which is defined by this. Then, of course, from this inequality, x, y1, y2, yn, we obtain the following inclusions. P x lambda, py1 dot lambda, py2 dot lambda, pyn dot lambda. And by combining this inclusion with this inclusion, we obtain n dot p is contained in this Minkowski sum. And we see that n dot p is contained in this Minkowski sum, which is equal to n dot px dot lambda. And then by dividing both sides by n, we obtain this estimate. So thus we have obtained this theorem. Let lambda be a dominant co-weight, and let X be a minimal octet representative. And if P is an element of the Demazure crystal associated to X, then we have a HR. P is contained in this extremal NV polytope, Px dot lambda, which is a convex hull of this set. And we recall the following remark. The converse statement does not hold in general. So this is the combinatorial part, and the following is the geometric part. We first recall some geometric setting. Let G be a connected, almost simple algebraic group over the complex numbers with the algebra G. And let B be a broad subgroup, T a maximal torus, and U unipotent radical of B. But it corresponds to negative roots. This is our Klein convention. And let K be a field of formal Lorentz series, O a ring of formal power series, and G the affine Grossmanian associated to G with a natural invariety structure. And let pi denote the quotient map from GK onto the affine Grossmanian G. Then we continue some notation. Let X star T the co-weight lattice, and X star T positive set of dominant co-weights, and X upper star T weight lattice. And we denote by delta positive as a set of positive roots. And for each new dominant co-weight, which is regarded as an element of this set, and which is regarded as a subset of this set, we denote by, so this element determines this element. So we denote it by T nu, which corresponds to this nu by these inclusions. And we denote by T nu descent of this element to the affine Grossmanian, and set G upper nu, the G is the GO orbit of T nu, and S sub nu the UK orbit of T nu. So we know the following due to Mirkovic-Vilonen and Lustig. For each dominant co-weight lambda, we have dimension G lambda is equal to 2 times lambda rho, where 2 rho is equal to sum of all the positive roots. And also we recall the following well-known fact. Due to, maybe this, of course, for example, due to Beilinson-Drinfeld, we have the GO orbit decomposition of the affine Grossmanian. They are denoted by G lambda, and note that GW lambda is equal to G lambda for W. So this orbit only depends on the Weyl group orbit. And we have the UK orbit decomposition of G. These are parameterize the co-weight lattice X star T. And G lambda bar is equal to the disjoint union of G lambda dot, where lambda dot is satisfies this relation. And where this relation is defined by this usual dominance ordering. And the S nu bar is equal to the disjoint union of these elements. Note that the opposite inequality appears because of our sign convention. So here, this means, of course, the usual dominance ordering. So we give a geometric definition of MV polytopes. In Sadaki's talk, a combinatorial definition is given in terms of Lustig datum. But the original definition of MV polytopes is geometric, and it's due to Anderson. Now let lambda be a dominant co-weight and nu a co-weight such that T nu is an element of G lambda bar. Yeah. So this condition implies if this condition means nu is a weight of the reducible highest weight module of weight of highest weight lambda, and we set Z lambda nu to be the set of reducible component of this intersection variety, which is all contained in G lambda bar, and call an element of this set Z lambda nu an MV cycle, Mirkovic-Vilonen cycle of highest weight lambda and weight nu, or an MV cycle for G lambda bar at nu in terms of Anderson. And definition, the following geometric definition, original definition is due to Anderson. Let lambda be a dominant co-weight and nu co-weight be such that T nu is an element of this G lambda bar. And then we set MV lambda nu to be the set of PB, where P is an element of this set, where and PB is a convex hull of nu dot, such that T nu dot is an element of B. This is a so-called moment map image of the MV cycle B, and call an element of this set an MV polytope with highest weight lambda and lowest with highest vertex lambda and lowest vertex nu. This is the original definition of MV polytope due to Anderson. And the Kamenitza's result says for each new co-weight and WBN wire group element, we set S nu W to be this orbit under this subgroup of GK. And remark that for new dominant for new co-weight and wire group element W, we have, of course, this, which is a restatement of some facts by Beilson, Drinfeld. Let us recall it. Because this S nu bar is equal to this set, so of course this S nu W bar is equal to this set. Moreover, we have P, the moment map image of S nu bar, S nu W bar, which is defined by this. This is a definition. Then we have this equality. So recall from the previous talk, Sadaki's talk, that we have P mu dot is convex hull of these vertices mu W indexed by wire group. And this is identical to the intersection of this shifted cone, where P mu dot is a pseudo-wire polytope with GGMS data mu dot. So, yeah, in this case, we know the picture is as follows. Let mu E like mu S1, mu S1, S2, mu W 0, mu S2, S1, mu S2. So all the shifted cone are of this form. This form and this form and this form, this form. Shifted cone is, is always of this form and shift by here, by here. And we consider the intersection of all these shifted cones. Then we obtain a convex polytope, and which is nothing but the convex hull of all these vertices. So here, thank you. So this means that this polytope is the intersection of all shifted cones, and this means that this polytope is a convex hull of its vertices. And this means that this shifted cone is a moment map image of this S nu W bar. This is a geometric meaning of this equality. So now the following fact, important fact, is due to combinatorial. The definition above MV polytopes, the geometric definition above of MV polytopes due to Anderson agrees with the definition of MV polytopes in the previous talk by Sagaki. And the previous definition is due to also combinatorial. Moreover, if mu dot is a GGMS datum of MV polytope P, that is P is P mu dot, then the variety B mu dot, which is defined to be this the closure of this intersection, is an MV cycle of highest weight lambda. Lambda is defined to be mu W0, and weight nu is defined to be mu E. Thus, the assignment P mu dot to B mu dot gives bijection from MV lambda to Z lambda, where MV lambda is a set of MV polytopes and Z lambda is a set of MV cycles, such that phi lambda MV lambda nu is equal to Z lambda nu, weight preserving. So, to consider tensor product of MV polytopes or MV cycles, we introduce some twisted products or convolution diagrams. We set G times tilde G to be this set, GK times GOG, which is defined to be the by this equivalence relation. ABGO is equivalent to AG, G inverse BGO for G in GO, and denoted by pi 1, the first projection given by this, and M by the multiplication map given by this. So, and we also introduce some twisted products for variety X, subvariety X of G, and the GO stable subvariety Y of G. We define X times tilde Y to be this set, where X tilde is pi inverse, the inverse image of X under the this quotient map pi. Pi is a quotient map from GK to the Affingerosmanian G. And similarly, for mu1, mu2 co-weights, we define S mu1, mu2 to be this twist product, which is a subvariety of G X G times tilde G. Then we know the following theorem due to Mirkovic-Vilonen and Lustig. Let lambda 1, lambda 2 be dominant co-weights, and nu also a dominant co-weight. Then the image of G lambda 1 bar times tilde g lambda 2 bar under this multiplication map M is equal to g lambda 1 plus lambda 2 bar. And this set, this inclusion, note that this is non-empty if and only if lambda 1 plus lambda 2 is greater than or equal to lambda. And in this case, the dimension of this intersection is given by this formula. And also we call the following fact, which is due to Ngo and Popolo. For each mirror co-weight, we have the inverse image of S mu under the multiplication map is disjoint union of these S mu1, mu2. S mu1, mu2 is defined by this. Then we have this decomposition of the inverse image of S mu. Moreover, for each lambda 1, lambda 2 dominant co-weight and mu1, mu2 co-weight, then the intersection, this intersection is a union of reducible components of dimension lambda 1 plus lambda 2 minus mu1, mu2 rho, where rho is half the sum of all the positive roots. So, yeah.
Just the double coset, or G lambda is it closed or not?
Oh, no, not close. This variety is not close. So, in order to prove our first result, which is an estimate of tensor products of MV polytopes, we need some reformulation of Braverman-Gates-Gorry's results. Braverman-Gates-Gorry's results. Let lambda 1, lambda 2 be dominant co-weights. Recall the following decomposition, tensor products, decomposition of MV lambda 1 times MV lambda 2 into connected components MV lambda with multiplicity M lambda, lambda 1, lambda 2. And if P1 is an element of every lambda 1 and P2 is an element of every lambda 2, then there exists a unique reducible component MV lambda with this, such that P1 times P2 is in this connected component. And also recall the bijection due to Kamenitzer from MV lambda to Z lambda, from MV polytopes to MV cycles, given by P mu dot to B mu dot. Then, the reformulation of Braverman-Gates-Gorry's result reads as follows. Let lambda 1, lambda 2 be dominant co-weights. Then there exists a bijection phi lambda 1, lambda 2 from MV lambda 1 times MV lambda 2 to the disjoint union of these sets of irreducible components, such that for each P1 and P1 in MV lambda 1 and P2 in MV lambda 2, we have phi lambda 1, lambda 2, P1, P2 is a subset of the inverse image of phi lambda P1 times P2 under the multiplication map M. And this phi lambda 1, lambda 2, P1, P2 is an irreducible component of this intersection, where P1 times P2 is of course, is in this connector. Maybe we call this, where P1 times P2 is in this connected component. So, from this result, with some technically complicated method, we can prove our first approximation result for the tensor products MV polytopes. But the technical argument is very complicated. I don't want to explain it here. But the main point is the proof. The proof of this reformulation is given by defining phi lambda 1, lambda 2, p1, p2 is defined to be phi lambda 1 tilde times u of phi lambda 2, p2, where phi lambda p1, p2 is inverse image of this set under the quotient map from GK to the Affine-Grassmannian. So pi is, because that pi is GK over GO, which is the Affine-Grassmannian. So note that here UO appears, and we recall that I forgot to mention here I forgot to mention the following. Thank you. For dominant co-weight lambda, G lambda bar, which is nothing but GO orbit, G lambda bar, and for while group element, G lambda intersection SW here, lambda. The closure of this is nothing but GO orbit TW lambda. The closure. Yeah. So, no. NO orbit. So, this is irreducible, and the moment map image of this is the extremal MV polytope. And so here NO appears. And in this definition, also, U, yeah, no, not the M, not U, U. Yeah, UO appears. U appears. So, so you can see one reason why we need the assumption that the MV polytope P2 to be extremal. If P2 is extremal, then this is NO, the closure of UO orbit. So the proof is very simple. But in general, I hope that the theorem, the approximation theorem, also holds without the assumption on the P2 to be extremal. But for the moment, we have the assumption that the P2 is extremal. So in that case, P2 is the moment map image of this variety, connected variety. So, yeah. So now we go also. Finally, we give one picture of MV polytopes. This is in type A3 and highest weight row check. Then the extremal MV polytope PW0 check is this, a parameter hadron, which is called parameter hadron. Yeah, so thank you for hearing.